Salt water conducts electricity. You probably learned that in school and then promptly forgot it because nobody told you the second half of that sentence. The second half is this. With 2 pieces of metal and a jar of salt water, you can generate a real measurable electrical current. Not a science fair trick, not a metaphor. An actual voltage you can put on a multimeter, feed into a circuit, and use. People have been doing exactly that for over 100 years. The method isn't complicated. The materials cost almost nothing. And the reason most people have never heard of it as a practical skill has everything to do with how the modern energy economy got built, and almost nothing to do with whether it works. Between 1908 and 1931, the U.S. Patent Office processed over 400 applications related to saltwater galvanic cells, low-cost, self-sustaining power sources built from materials anyone could find. These weren't fringe inventors. Some were university chemists. Some were industrial engineers working for companies that manufactured telegraph and telephone equipment. The galvanic cell, a device that converts chemical energy directly into electrical energy using metal electrodes and a liquid. Electrolyte was a known, documented, and widely used technology. Alessandro Volta had demonstrated the core principle in 1800. By 1920, the zinc-copper saltwater cell had been refined to a reliable, reproducible design. Field manuals from that era describe it plainly. 2 plates, 1 solution, continuous current. The U.S. Army Signal Corps included saltwater cell construction and training materials through the mid-1930s. Remote telegraph stations in the American West used variations of this setup when grid power wasn't available, which was most of the time. This wasn't obscure knowledge. It was practical knowledge, the kind that gets passed down through working trades. And then, quietly, it stopped being passed down. Here's what's actually happening when you drop 2 different metals into salt water, and why this specific pairing of metals is everything. Salt water is a conductive solution. Table salt, sodium chloride, dissolves into sodium and chloride ions, which means the water itself becomes a medium through which charged particles can move. When you place 2 metals into that solution, something interesting happens at the surface of each one. Different metals have different tendencies to lose electrons, a property called electronegativity, or in practical terms, their position on the galvanic series. Zinc is electropositive relative to copper, which means zinc wants to give up electrons more readily than copper does. When both are submerged in the salt water, zinc starts to oxidize. It releases electrons into the external circuit while zinc ions go into solution. At the copper plate, the opposite reaction occurs. Electrons arriving through the external wire react with ions in the solution, completing the circuit. The salt water isn't just sitting there, it's actively carrying ions between the 2 plates, maintaining the electrochemical balance that keeps current flowing. The result is a continuous flow of electrons from the zinc plate through whatever is connected to the circuit and into the copper plate. That electron flow is electricity. The voltage produced depends on the electrochemical potential difference between the 2 metals. For zinc and copper, that's roughly 1.1 volts under ideal conditions. Predictable, repeatable, explainable at the molecular level. This isn't magic, it's 19th century chemistry that still works exactly the same way it did in 1920, because physics doesn't change. Rural electrification in America wasn't just about bringing power to farms, it was about making farms dependent on a billing infrastructure that hadn't existed before. The Rural Electrification Administration, established in 1935, did something genuinely transformative. It extended grid power to parts of the country that had been generating their own electricity, or doing without. But extending the grid also meant extending a payment model. Once a household was on the grid, they stopped maintaining the skills and equipment they'd used before. Saltwater cells, wind chargers, and local gas generators didn't disappear because they stopped working. They disappeared because the economics of scale made grid power cheaper per kilowatt hour, and because once grid dependency was established, the older methods were no longer taught. By 1950, the galvanic cell had migrated from practical field manual to chemistry classroom curiosity. The knowledge hadn't been suppressed in any dramatic sense. It had simply been deprioritized. Nobody profits from teaching someone to generate their own power from a jar of salt water. The power company profits when you use theirs. That's not a conspiracy. It's just how economic incentives work. The result, though, is that most people alive today have no idea how to do something their great-grandparents could have done in 15 minutes. The original design used 3 components: a zinc plate, a copper plate, and a saturated saltwater solution. And the measurements matter more than most people realize. Let's go through this carefully. Your zinc electrode should be a strip of pure zinc, approximately 10 centimeters long and 3 centimeters wide, and at least 2 millimeters thick. Hardware stores sell zinc flashing for roofing. That works. Zinc anodes sold for marine use are even purer and work better. Avoid galvanized steel. Galvanized steel has a zinc coating, but the steel core will interfere with the reaction once the zinc layer is depleted. You want solid zinc. Your copper electrode should be a similar size, 10 by 3 centimeters, at least 1 millimeter thick. Copper pipe cut lengthwise works. Copper sheet from a craft or hardware store works. What you want is uncoated, unplated copper with maximum surface area exposed to the solution. The container should be non-conductive. Glass or ceramic is ideal. Plastic works. You don't want metal. Fill it with salt water made from 35 grams of non-iodized salt per liter of room temperature water. That's roughly the salinity of seawater, which is the concentration at which conductivity is near its practical peak. Go higher and you don't gain much. Go much lower and your internal resistance increases and your output drops. Suspend the two plates in the solution so they're fully submerged but not touching each other. The distance between them matters. Closer plates mean lower internal resistance and slightly better current output, but you don't want them in contact or you'll short the cell. A separation of 2 to 3 centimeters is workable. Connect your measuring device or load to the two plates using wire clipped to the exposed upper portions. Zinc connects to your negative terminal. Copper connects to positive. When you first connect a multimeter across the terminals with no load, you should read somewhere between 0.9 and 1.1 volts. That reading will drop slightly when you connect a load. That's normal. It's called terminal voltage versus open circuit voltage, and every real power source does the same thing. The current output of a single cell this size will be somewhere between 1 and 5 milliamps depending on electrode surface area, solution freshness, and temperature. That's not a lot yet, but it's real, measurable, and consistent for days before the zinc begins to deplete noticeably. Let's be precise about this because honest numbers are more useful than hype. A single saltwater galvanic cell produces between 0.8 and 1.1 volts. At the current levels a single small cell can sustain, you can power an LED directly. A standard red or white LED requires about 1.8 to 3.3 volts forward voltage, so you'd need at least 2 cells in series to reliably light one, but once you have that, it runs continuously for days, without batteries, without solar panels, without grid power. That's not trivial in a camping scenario, an emergency situation, or an off-grid application where you need a basic indicator light. A single cell can also trickle charge certain types of capacitors for burst applications. It can power extremely low draw sensor circuits. Some older analog clocks run on less than a microamp. A properly built multi-cell saltwater stack can handle those. What a small cell stack cannot do, to be direct with you, is run a phone charger, power a laptop, or run any appliance. The current output is simply too low for those applications without a cell array that becomes impractical to build at home. Knowing what it can and cannot do is what separates this from mythology and puts it in the category of genuinely useful supplementary knowledge. Cells in series add voltage, cells in parallel add current, and understanding that one principle is the difference between powering an LED and charging a phone. If you build 4 identical zinc copper saltwater cells at 1.0 volt each and connect them in series, positive terminal of one to negative terminal of the next, your total output is 4.0 volts. That's enough to begin charging a small lithium cell through a simple boost circuit, though at the current levels you're dealing with, it will be slow. Connecting cells in parallel instead keeps voltage constant at 1.0 volt, but adds the current of each cell together, giving you more power at the same voltage. Useful if you need to sustain a low voltage load for a very long time. The practical sweet spot for most off-grid emergency applications is a 4 to 6 cell series stack, enough voltage to do useful work, combined with 2 to 3 of those stacks in parallel, giving you a 4 to 6 volt output with enough current to charge small devices overnight through an appropriate circuit. The zinc plates will deplete over time as they oxidize. In a well-built cell with proper electrode dimensions, you're looking at meaningful output for several days before performance drops noticeably. Zinc plates can be replaced, the solution can be refreshed. The copper plates last indefinitely if kept clean. The entire system, once understood, is self-maintaining with basic materials. The reason this method never disappeared completely is that physics doesn't take funding. The galvanic cell works in 2025 for exactly the same reason it worked in 1920. The electrochemical potential difference between zinc and copper is a physical constant. Nobody can update it, discontinue it, or require a subscription to access it. What this method represents, practically speaking, is a baseline electrical capability that exists outside any infrastructure. No grid, no fuel supply, no manufactured component you can't eventually replace. For a certain category of use, remote sensing, emergency lighting, off-grid indicators, educational demonstration, it's genuinely useful today. More importantly, it's the foundation of understanding that makes larger electrochemical projects accessible. Anyone who can build and troubleshoot a saltwater cell understands enough about electrochemistry to work with more sophisticated battery systems, fuel cells, and energy storage technologies. If this kind of foundational infrastructure-independent knowledge matters to you, the things that work regardless of what's available at the store or what's running on the grid, there's a lot more in this territory worth exploring. Subscribe and you'll catch the next one. And if you've actually built a galvanic cell or used one in a real application, drop it in the comments. I want to know what you powered with it.